thanks to all of you for surviving the first talk and coming along to the second one. Let me remind you of, get started again. I'll start with the fundamental theorem of Neumann. So we're talking about, we have a Hilbert space, and we're talking about the star algebra of all bounded operators on the Hilbert space. And we have this notation that S is a subset of DH. S prime is the centralizer, commutant. And we have the abbreviation notation. The commutant of the commutant, we just put 2 primes. Okay, so last time I stated the theorem. Due to von Neumann and known as a von Neumann density. And it's the following conditions are equivalent. We have to have some data. M star cell. We're given a star subalgebra B of H containing the identity, then following the equivalent. The first one is that M is strongly closed. Now this is, so I remind you that strongly means this, the topology of pointwise convergence on the Hilbert space. Well, if you like semi-norms, you can define some psi norm of X for psi vector. These semi-norms generate a topology and it's the convergence in that topology. Second question is, second one is that M is weakly closed. And this is pointwise weak convergence. And you can also define it in terms of semi-norms, probably by such a thing. And finally, the third condition, purely algebraic, nothing to do apparently with convergence, that M is actually equal to its second commutant. So this is called the density theorem for the following reason. For tautological reasons, just semantics, M is always contained in the second commutant. The commutant is, this is, by definition, this is the set of all things that commute with everything that commutes with M, and obviously M commutes with everything that commutes with M. So what this is saying is that if you take this subalgebra of the second commutant, then, and you take its closure, then you get take the closure in either of these topologies, you get the second commutant. So that's why it's called the density theorem. It's non-trivial even in finite dimensions, and I believe that the history is that von Neumann proved it initially in infinite dimensions, and I think Jacobson or someone like that took his proof in infinite dimensions and adapted it to finite dimensions, where it's become an integral part of this semi-simple theory of semi-simple algebras. So for us, it serves simply as a definition springboard for the definition of a von Neumann algebra. A von Neumann algebra is, by definition, a subalgebra of B of H containing the identity satisfying any one of these three equivalent conditions. Okay, and yesterday I gave you some examples of von Neumann algebras, and I gave you some important non-examples also. The first example is B of H itself, actual example, which is tautologically, with any of those three definitions, it is obvious that it's a von Neumann algebra. So this includes, of course, in finite dimensions, the full matrix algebras. And the second example was L infinity. A measure space acting on L2 of a measure space, that's always a von Neumann algebra, and this is this one, of course, is highly non-abelian. It's an exercise. Show that the center of B of H, which in this case is also the same thing as the commutant of B of H, is C plus Z. So this is an exercise that you can show without too much trouble, that if an operator, bounded operator, commutes with all other bounded operators, then it has to be a multiple of the identity. So this is highly non-commutative. This example is completely commutative. Right. So these are going to be our starting examples, and then there's a theorem of von Neumann once again. That any abelian von Neumann algebra is this form. Now I'm actually sweeping up under the rug something. I'm sort of hiding something that's not necessarily very pleasant, which is the multiplicity question. This L infinity on L2 of x mu is you could think of it as one way of representing the algebra L infinity, but there are lots of other ways with multiplicity, and you can see that perfectly fine in fine dimensions that happens. But so when I say of the form, this sort of means up to multiplicity. To really fully understand this, you have to know about spectral multiplicity. But abstractly, certainly the algebra, the von Neumann algebra, looks exactly like this one. So given an abelian von Neumann algebra, there is a measure space such that the algebra is isomorphic to L infinity of x mu, but perhaps not to L infinity of x mu acting on this Hilbert space. They will be acting on another Hilbert space in general. So this is von Neumann's theorem. It's really another version of the spectral theorem, because von Neumann showed that in the separable case anyway, maybe this isn't even only true in the separable case, any abelian von Neumann algebra is generated by a self-adjoint element, and so you just apply the spectral theorem to that element and you obtain this result. Right? So that's very nice. This theory, if one was interested in the study of all von Neumann algebras, we've made a very good start. We know all commutative von Neumann algebras. And mathematically, that's very nice, because there's a sort of general mathematical philosophy that if you want to study something, you study the commutative case first, and then to study the non-commutative case, you get as large as possible a commutative subalgebra. And try to reduce the study of the whole thing to that. All right. So we've done this. Now the immediate consequence is for this is that if you take any full Neumann algebra, any full Neumann algebra, once again on a separable Hilbert space, then the center of M is actually equal to L infinity of x mu. The center of M is, there is a measure space such that the center is the L infinity functions for that measure space. And then there is this theorem due to von Neumann, once again, that what this means is that M, I'm going to illustrate this in finite dimensions, so you're supposed to understand the meaning of it from the finite dimensional case. That there's some way that you can decompose the whole von Neumann algebra as not a direct sum but a direct integral of M of x dx, where we have got rid of the centers. So the center of this is triple. Right? I mean, in general, you see, the point is that if you have a von Neumann algebra and it has some center, then you can take a projection in that center and just sort of chop everything down. You get a smaller von Neumann algebra. And you would try to get rid of the center altogether just by taking smaller and smaller projections. Well, in the continuous world, you never really necessarily get down to atoms, at least in no easy way. But von Neumann showed that if you do it carefully, you can sort of get down to atoms, and you can write your Neumann algebra is a direct integral, whatever that means, of x of M of x dx. Right, so what does this direct integral mean? Well, I just want to illustrate in finite dimensions where it's quite simple process. So if we have M is a algebra acting on a finite dimensional Hilbert space, it would work for a finite dimensional algebra on an infinite dimensional Hilbert space as well. Then we look at its center, and this von Neumann theorem says that it has to be L infinity of x mu. But since the dimension is finite, x mu is just some finite set. So the center, therefore, this is just L infinity of x mu is just a function from some set, some finite set. And I want to think of this in another way as being C, direct sum C, direct sum C. Okay, this is just another way of saying the same thing. And I want to write this in another way as P1C plus P2C plus, where Pi, what's called a partition of unity, atoms, these are all words with nice emotional content. So these PIs are minimal projections. If you start cutting down, looking at projections in this, if you start looking at projections in this algebra, then the projections just correspond to finite subsets here of the decomposition. And if you want to get a minimal one, the minimal ones are obviously when you can't go any further. And so this would be a minimal projection corresponding to this. I can also write it. The first one is 1, 0, 0, 0. The second one is 0, 1, 0, 0, and so on. All right, these are all different ways of saying the same thing. hopefully one of them will make you understand what's going on. But the point is that since they're minimal in the center, when you take P1, you take PI ZM, sorry, M PI, you get something with no center. If it had a center, well, you get a smaller projection. Okay, you just look at that, the center of that, and decompose it in this way, and you get smaller projections. Okay, so the conclusion, since the PIs are in the center, we find that M is equal to the direct sum of PI M. Since the PIs commute with anything, I can put that on the left or the right, either side, or both sides. So this is the direct integral of a set consisting of 1 and n. Well, just put counting measure on this thing. Right, so the von Neumann theorem here is a fancy continuous version of this very simple decomposition in finite dimensions into subalgebras, PIM, PI, which have trivial center. That's the point. Now, it's actually an easy exercise in finite dimensions to show that the von Neumann algebra of trivial center is actually a full matrix. Some n by n, some n. Analysis goes by actually trying to find minimal projections in that. So we end up with the final result that in finite dimensions, M is equal to a direct sum of matrix algebras of various sizes. This is our complete analysis of von Neumann algebras in finite dimensions. Any von Neumann algebra in finite dimensions is direct sum of full matrix algebras. And if you're an algebraist, this is a simple case of the Wedderburn theory of semi-simple algebras. This condition that von Neumann algebra, that's a star algebra, implies semi-simplicity in finite dimensions, and you could have deduced this from the general theory. Okay, so it's important. Now we understand all von Neumann algebras in the abelian case, all von Neumann algebras in the finite dimensional world, so we've made the obvious good start on understanding all von Neumann algebras. Okay, obviously a big role is being played by von Neumann algebras with trivial center, right? The idea was that we tried either very naively in finite dimensions or a much more sophisticated way in infinite dimensions to reduce the von Neumann algebra, the whole thing, into von Neumann algebras, sort of these little nuggets. I won't call them atoms because they're not really atoms here, but little nuggets, and the nuggets have trivial center. We've got rid of all the center. The idea is simple. If one of these had any center, then we could further reduce the whole thing. Okay, so this calls for a definition. Factor. And why is it called a factor? Well, the reason is because I'm going to give you an example. Now I showed that B of H itself, that was an exercise, is a factor. The exercise should show it has a trivial center. But what we can do is we can take a Hilbert space, and we can suppose Hilbert space itself is a tensor product of two Hilbert spaces. Very sort of quantum physics relevant thing to do. And what it is that we can let V of H act on this by V of H tensor identity. So we have two obvious algebras here, B of H1 tends to the identity and the identity tends to B of H2. Okay, so these are operators that act on here, tends to something by the identity and the other one. Well, these two subalgebras are actually factors. Factors. Abstractly, they're nothing but some B of H, but they're acting on a bigger Hilbert space than their own Hilbert space. So this is just B of H acting on, amplified to act on a bigger Hilbert space. So these are factors, and so we see that these factors correspond to a tensor product factorization of the Hilbert space. That's where the name comes from. And when you read the original papers of Murray and von Neumann, you get the feeling that what they started out trying to do was to show that every factor corresponds to a factorization of the Hilbert space in this way. Okay? That feeling, I guess it's never explicitly said, but it sort of permeates the philosophy of the first couple of papers. So obviously the implication is that it's not true, right? So now what I'm going to do is show you that you can get factors that don't correspond in this way to a tensor product factorization. So this was the first really major discovery in the work of von Neumann and Murray and von Neumann. So I think in order to get started on this, we have to sort of reboot. Out. Okay, so let me just in a few words try to resume the whole program so far. We're trying to study, we've got this definition of von Neumann algebras, very natural, nice theorem to start the program. We're trying to study them all. So first case is we've looked at abelian ones. We've decided that we understand abelian ones as well as we understand measure theory. They're L infinity functions in some measure space. Then applying that to the center of a von Neumann algebra, we've reduced the study of all von Neumann algebras via this direct integral construction, which is easily understood in finite dimensions, to the situation where the centers of the von Neumann algebras are trivial. We've called them factors. And we've noticed that factors can come from tensor product factorizations of the Hilbert space. And if you have such a factorization of the Hilbert space, you have two natural factors. I should perhaps add that these two are each other's commutant of this. Also in the realm of exercises, matrix decomposition. Okay, any questions about that? Now we're going to start a new sort of chapter because we're going to, our first goal will be to exhibit factors that do not come from factorization of the Hilbert space. This is going to come from groups. So I want to come back in the spirit of the beginning of this course, do something extremely elementary and extremely concrete and understandable, hopefully to everyone. We're going to consider the cyclic group Z mod n Z, and we're going to consider what's called its regular representation. If the group was commutative, we would have to talk about the left regular representation. If it was not commutative, we would have to talk about the left. But since it is, that's all we have to talk about. And what is this? Well, this is acts on, in fancy words, the L2 space of Z mod NZ, but that's just a, you know, really super fancy way of saying just functions of vector space of dimension n. And the representation is simply, if you like, this space has a basis, epsilon 0, epsilon 1, epsilon n minus 1. Linear spans of this. This is an orthonormal basis, and the group acts simply by cyclically permuting this basis. So if we take, we call the generator of this one, we call it 1, then the group, then, and we call the regular representation U sub 1. So this is going to be unitary on this vector space, which represents, translating by 1, then U sub 1 epsilon I equals epsilon I plus 1 mod n. I'm saying something which is incredibly elementary here, so if you have any questions at this stage, you better ask me, because this is just a question of notation. Okay? Everyone's good. All I'm taking as a vector space, dimension n, and I'm cyclically permuting the basis elements. All right? Well, and I'm calling this the regular representation of this. And, you know, if this were not 1 but some other number, this would be I plus k. U sub k, this would be I plus k. So in UK is U1. Okay? So what everyone has to know is something completely trivial, which is what is the matrix form? What does this U sub 1 look like as a matrix? Well, it takes the first vector and shifts it along like that. It takes the second vector and shifts it along like that. It takes the third vector and shifts it along like that, and takes the last vector and it comes back down here. Okay? So this is the matrix of U sub 1. So what we say is that it's, you know, we think of the places where it's 1 as being some kind of diagonal. The diagonal is the main diagonal. We're thinking of this one as being kind of diagonal, right? Now, we're interested in algebras, so we want to extend this representation to the group algebra, Z mod NZ, which means we simply take linear combinations of such elements. So this is U1. U2 would be the element with where the ones would be shifted by 1, right? U2 would have U sub 2. Yeah, right. U sub 2 would have 0, 0, 1, 0, 0, 0, 1, and we'd have a couple of 1s down here. Okay, so this would be the diagonal corresponding to U2. This is the diagonal corresponding to U1. And if we take a linear combination, sigma Ci Ui, what does that look like? Well, it looks like, very simply, there'll be C0 down the diagonal. There'll be C1 down the second diagonal. Matrix. C0, 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 C. Okay, so 4, C1, 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 C2, C2, C3, C2, C2, 3, 3, C3. Okay? The point is, and I really want to drive this home, that it's constant along these diagonals. Constant there, constant there, and it's constant there. Where's what happened to the C2s? And then there's the C3s. Okay? So it's very trivial, very hands-on. Now, I want to now start to generalize this and look at a more complicated situation. First thing we could generalize is that the group is not commutative, okay, or not cyclic. So what happens there? Well, the same thing, the same form will be true, except that these diagonals, instead of just being straight down like that, they'll be a bit more scattered. In fact, for a given group element where the thing is 1, this is actually generating the Cayley multiplication table of the group. Okay? So, I mean, for instance, with Z mod 2 plus Z mod 2, the diagonals would be this, and some other diagonals. Anyway, so you can imagine that all that happens if you change to a different group is that these diagonals have a slightly more complicated structure. They're not quite as don't sit as well. Otherwise, if you take linear combinations, same is true. Okay? Terrific. So now what we're going to do is take the big step and say what if the group is infinite. So, what if we go? So we've started with Z mod n Z, where we understand absolutely everything, to G, some arbitrary finite group, now to some infinite discrete group. Well, once again, U of some G, so now the only, we're looking at on the Hilbert space L2 of G. Since it's infinite, let's call it gamma. Fun. We're looking at the Hilbert space L2 of gamma, but the regular representation, this left regular representation is the same thing. This is going to be some 1s in various places, right? Where the places where it's 1 is this what I've called a diagonal. In the case of Z, this would just be the sort of one away from the main diagonal. But in general, for an arbitrary group, it's like this. So now, if we take linear combinations of CG, the sum, a finite sum, or over the group of constant CG, okay, then what does that look as a matrix? Well, what happened in the finite size was that the CGs were displayed along these diagonals, same thing. The diagonals are infinite, but the matrix will be simply the same. So this will be, we'll have CG down the CG diagonal, whatever it looks like. And we'll have CH down the CH diagonal, whatever that looks like. And of course, C to the identity down the main diagonal. And mostly because this is finite sum, it'll be 0. So outside of a sort of band, if you like, it's going to be everything's going to be 0. Okay. So far, I've sort of done nothing. All I've explained to you is but it's really crucial, what the matrix of a linear combination, finite linear combination of left regular representation things looks like. Okay. There are these diagonals. And the element, the operator representing this linear combination is constant down those diagonals. All right. Now I want to take the main step, and this was a step taken by von Neumann. And the way I prepared it is going to look trivial, but to actually see this was a huge observation, really, when you think about it. We want to consider what happens when we take the von Neumann algebra generated by these guys. We want to take the weak closure. Okay. Well, it's a sort of difficult, subtle thing to take the weak closure of an algebra. You may pick up all kinds of bizarre things in the limit. But think about the matrix coefficients. The matrix coefficients are things of the form x psi eta. These are precisely the things that we control in the weak topology. These are the defining seminorms of the weak topology. So the point is that if you take a weak limit of such operators, then that weak limit will also have the property that the C's are constant down these diagonals. Okay? So if we take the weak limit, so here's the big deal. We've got the group algebra, if you like, this is an element of the group algebra of gamma. C gamma. It's from finite linear combination of the UGs. It's displayed all of these things as matrix coefficients. In a weak limit, of such operators, we'll have the property that the coefficients are constant. So what does something in the weak closure look like? Well, there are CGs. Now CGs not just for a finite set, but for all elements of the group. And the matrix looks like this, except there's not everywhere zero. There's not necessarily any big zero chunk. So the only effect of taking the weak limit is to get rid of this fact that they're almost all zero. Right? So an element of the weak closure, we could still naturally write it as some sum of G belonging to gamma of CG UG. Okay? Well, what we mean by sum is simply the following. We look at the matrix is constant down these diagonals, these G diagonals, and we pick off the term with for that G. So we've done something that is morally no more complicated than this original case of the cyclic group. But this is now in the weak closure. Anything in the weak closure looks like this. The sense in which the sum converges, perhaps we don't know much about that, but certainly there is a function, and we have a natural right to use this notation that it's the sum, even if we don't really know what it is. Okay? So the obvious question arises, we've seen this sort of question before, is what functions G delta CG? When we take a weak limit of one of these things, we'll get a function. But what kind of function are we going to get? Well, that's a bit tricky. It's very tricky. It's sort of a hard subject, really. This algebra study really focuses. Maybe 90% of the work on polynomial algebra in the last 40 years has focused in some sense on that question. What are the functions from G to CG that you get? One case where you can figure it out is if the group happens to be commutative, if the group happens to be Z, then the functions are, by Fourier analysis, they're Fourier transforms of L-infinity functions. Very simple. This is the question of what functions you get is some kind of generalization of what functions on the integers are Fourier series of L-infinity functions. Okay, now I want to come to the point. We've had this big digression. We've been very, very concrete. Okay, we've looked at operators as matrices, and we've gone from finite-sized matrices to infinite ones. The only thing that's a little bit that we haven't really done made sense of is in what sense that sum converges. However, there is one thing I'd like to point out that is completely obvious, and that is one condition, one necessary condition on the CG. So here's this fundamental and really deep question, sort of non-commutative Fourier analysis, in some sense, Fourier series. But there is one obvious necessary condition. Let's go back to that. Let's go back to the cyclic group case, a very simple case in finite dimensions, and we'll take this matrix and we'll apply it to the vector 1, 0, 0, 0. Okay? This is the epsilon, this is if you like epsilon 0. What happens to this vector? Well, what happens is obviously we get C0, C1, C2, C3. Okay? So when we apply the matrix to this particular vector, we see the function just coming out, right? We see these coefficients. Exactly, one for each element of the group. Fabulous. We do this in infinite dimensions, it's exactly the same. We apply our thing with the CGs to the vector. Now it's an infinite vector with all the zeros, and we get C of the identity element and CGs down here. Okay? So if we want to actually see what these CGs are, we can get them simply by applying the operator to a certain vector. But we're in Hilbert space, so this is L2. So the necessary condition on these CGs is that CGs, the function G going to CG, is right? So that's one thing. It's kind of fairly weak condition. It's necessary, but far, far, far from sufficient. But it's going to take us a long way. So let's examine the consequences of this if we want to work out the center of this algebra. We want the center. Right, remember, von Neumann has told us if you want to understand the von Neumann algebra, look at its center. First step. So if we look at the center of this algebra, what do we get? Center of this algebra. Let's call it something. Let's give it a name. Right, so I'm going to use my name, which is not the usual name. No one has followed my lead, but I think this should be called the von Neumann algebra of the group. So what have we done? We've taken the group, we've taken this group algebra, and we've taken the von Neumann algebra generated by it. So that deserves to be called the von Neumann algebra. Fortunately, that's not standard notation. Standard notation is L of gamma or U of gamma.
So gamma is G.
Sorry?
Gamma is G.
Yeah, gamma is G. I sort of did that. Yeah. For the psychologically, for the infinite discrete case, I'm calling it gamma rather than G. G is sort of a finite or compact group in one.
Yeah, I understand.
Yeah, I pointed out, sure. Gamma is the group. Center, so we're interested, von Neumann says, if you want to study a von Neumann algebra, look at its center, figure out what it is. So let's figure out what it is, von Neumann algebra of G. All right, well, any element in the von Neumann algebra has to be one of these given by one of these functions, sigma, CG, and G. And this is just a notation for the matrix where you have CG down these G diagonals. Okay, well, it's not hard to intimidate yourself into the following calculation. You can do this in a dozen ways, and it just obviously has to be true. But this is sigma CG UH G divided by inverse UG. Something like sigma, probably C HG H inverse UG. Okay, once again, the standard exercise is to sort this out, make sure the inverses are on the right side. Okay, so in other words, for one of these elements of the von Neumann algebra to be in the center, it's got to commute, if and only if it commutes with all of these UGs, because they generate the whole thing. So the condition is this. Okay. So what does this mean? This means that C is constant on conjugacy classes. Remember, when you have a group, you can split it up into the conjugacy classes, which is success as you get from starting with an element and conjugating it by everything else. Okay, this is of course very familiar to anyone who's done a course in finite group representation. The center of the group algebra is given by these conjugacy classes, and that's a number of irreducible representations and so on. But here, this is the conclusion we've come to. But now we're talking about big groups. So let's think about the conjugacy classes if we have the free group on two generators. Okay, how big are the conjugacy classes there? Well, if you take an element of the free group and you allow yourself to conjugate by anything, then since the group is free, you're never going to stop getting stuff, right? Unless you happen to be the identity element. So the freeness of the group implies absolutely immediately that all of the conjugacy classes are infinite, except that of the identity. All conjugacy classes. Except, of course, that of the identity. So what are the consequences for an element of the center? So we have an element of the center. It's given by one of these CGs, things down the funny diagonal. They're constant on the conjugacy classes. They're in little L2. Well, that's a real problem. To be constant on a conjugacy class and to be little L2, there's only one choice, and that's got to be 0. The conjugacy class is finite. The square, the sum of the squares has to be finite. So if it's anything other than 0, then it has to be, it wouldn't converge in L2. Conclusion for all of this is that CG equals 0. And that's so this is the fabulous conclusion. I took it very slowly because of this. At least I want you to understand as deeply as possible, as concretely as possible. The only CG that can be non-zero for something in the center of this algebra is the C of the identity. So what's the center of the algebra? Scalar multiples of the identity. So we conclude, the conclusion is that center of the polynomial algebra of the free group on two generators is C times the identity. It's a factor. Right, the only property of the free group that we used was this all conjugacy classes being infinite, and that's generally abbreviated ICC. If you take your favorite non-commutative group, it will almost certainly up to something trivial have infinite conjugacy classes. Braid group. But once you've got rid of the trivial stuff, will have infinite conjugacy classes. The infinite symmetric group, permutations, finitely supported permutations of an infinite set, obviously has infinite conjugacy classes. So all of these groups give examples of factors. Okay? And at this point, we can actually state sort of the sore thumb of the whole subject, I guess sort of the main outstanding question in polynomial algebras at the moment. We can actually state it. The shame, if you like, of the subject, we're unable to answer this question. Okay, so really simple question like that. Take these two polynomial algebras, one with a free group on 2 and one with a free group on 3 generators, then are they isomorphic? As algebras, star algebras, unknown. It has remained unknown. People have been trying very, very hard to solve this question. Years at least. So, if you I once talked to Hagerup about this question. Hagerup is one of the strongest people in the subject. And at one point he told me that his entire career had been devoted to solving this problem. Okay? All the other things he was just sort of offshoots. So, so don't expect to solve it very easily. Let's see, I won't really go into any more comments, except to say that the problem, if you didn't close it, the point is this. If you didn't take the weak closure, you just took the group algebra, then it's trivial. Okay? It's trivial. You can just count the number of algebra homomorphisms in the algebra. It's trivial that C of F2 is certainly not isomorphic to C of F2. Just take the number of algebra homomorphisms to the scalars or something like that, and because it's a free group, it's all over. So the problem comes in when you take these weak limits. And so we're immediately back at this problem here. What functions G to CG actually occur? So it's just the difficulty of this question is a reflection of the depth of that question, of the depth of Fourier series in this non-commutative situation. Okay? Right, so I've made a big deal about this being a factor, and I've, I would have been wasting my breath if this turned out to be a factor like the other ones. So remember that the reason we call these things factors is you've got interesting examples by taking a tensor product splitting of the Hilbert space in H1 and H2. Then you could put all bounded operators here tends to the identity, and the identity tends to all bounded operators. These are two factors, and this is a sort of factorization of the Hilbert space. Well, I want to convince you, and it won't be very hard at all, that for this factor, for polynomial algebra with trivial center, there is no such decomposition. Okay, and for that, all we have to do is define the following map. Trace from polynomial algebra of gamma to C to the trace of one of these matrices with CGs down the diagonal, which is simply C times the identity. C is the coefficient of the identity. Okay, so another way to think about this, which will be appeal to a physicist, I guess, is what does this matrix look like? Well, it's got these CGs down the diagonal. In particular, down the main diagonal, we see this number, this fixed number. Right, now we want to give it a trace. Well, the trace is supposed to be the sum of the diagonal elements. But, they're all the same. So if you add them all up, you're going to get infinity. But if you want to renormalize that, what would you call the trace? Well, there's an obvious candidate for the renormalized trace, which is you just take the coefficient, that number that you see down the diagonal. Okay? And that has the property that trace of AB equals trace of BA. That's a trivial calculation. And it also has the property that trace of 1 is 1. And it has actually a third property you need, and it's continuous. It's weakly continuous. It's continuous. Why is it continuous? Because this is actually a matrix coefficient, right? This is actually the same thing as, if we call this thing x, this is just x, psi, psi, where psi is our favorite vector, the one that has 1 here. This is the identity. So since it's this, it's manifestly continuous. Okay. And exercise, no such, and this really is an exercise, no such linear functional on B of H, dimension of H. So we have now completed the miracle, the von Neumann miracle. We have exhibited a factor which does not correspond to a factorization of the Hilbert space. Because if it did, we couldn't have such a trace. Okay. So we now have a definition. definition. M a factor trace what? These conditions here. I have three of them. Wrote it rather terrible, I'm afraid. Try to make this a little bit better. 1, 2, and 3. Satisfying 1, 2, and 3 is called. Well, I want to say 2, 1 factor, but that's not. I need to add infinite dimensional. Obviously, calling it 2-1 means there's other kinds. There's type 1 and type 2, and we'll talk a little bit about them. But this is going to be the focus of this course. Really is on various, well, it's on subfactors. So, but we're going to mostly, because of time, restrict ourselves to the 2-1 case. So why did I have to add this word infinite dimensional here? Well, you all know of a polynomial algebra, a factor with a trace satisfying all these conditions, and that's just the n by n matrices, right? That's the factor, that was the exercise, no center. The usual trace, if you divide by the dimension, satisfies these conditions. It's obviously continuous and satisfies those conditions. So to distinguish 2-1 factors, we don't want to call a finite dimensional thing anything fancy. We insist that in fact 2-1 factors are infinite dimensional ones having such a trace. So people are looking a little bit lost. It'd be nice to have some questions if anyone has a question. Okay. So to sum everything up, what we have done this morning so far, everything was focused on proving that phenomenon algebra of gamma is a type 2 factor, type 2-1 factor. Remember, phenomenon algebra of gamma was this very simple, quite naive construction of taking the left regular representation and taking the phenomenon algebra generated by it, linear combinations whose matrices have very nice form. Okay, so it's a convenient place to stop for a 15-minute break. So if you can, try to think a bit about that during the 15 minutes, because you're going to be taking off on these 2-1 factors. right, so we have the notion of the 2-1 factor. Now, 2-1 factors are really amazing beasts. They've seduced many a mathematician, including myself, and certainly including Neumann. Oh, sorry. So, and I want to emphasize the first wonderful feature of 2-1 factors, and that is we're going to study the following question. Remember 2-1 factors come with a trace. Okay? And what I want to do is I want to study this set, a set of real numbers. We want to take the projections, and we want to look at their traces. Okay? And what does this set of real numbers look like? Well, obviously it's contained in 0, 1. By the Cauchy-Schwarz inequality or something, if you have a projection, its trace must be less than or equal to 1. For some, perhaps not quite so obvious reason. Maybe I should say that the trace always traces a This is the so-called positive definite property of the trace. I could have, by the way, in this exercise here, I could have replaced continuity by that condition. Which still would have been true. So maybe I should have said that. Probably would have been smarter of me to point out this property rather than continuity. The trace of anything positive is positive. Okay. So, all right. So let's try to get some intuition for what it might be as a subset of the unit interval by looking at finite dimensions. What happens in finite dimensions? Well, as I said, we have infinite dimensions, the n by n matrix algebra certainly has a trace satisfying all of these nice conditions. We just normalize it so that the trace of the identity is 1. But then what's the trace of a projection? Well, a projection in finite dimensions, as I said, as we saw last time, is just some 1s down the diagonal and some 0s, and the trace of that is going to be, well, it's the number of 1s, but we've got to normalize it, so it's the number of 1s divided by n. So if we take the n by n matrices, what does the set look like? The set of traces looks like 0, 1 over n, 2 over n, 3 over n, n minus 1 over n, and n. So these 2-1 factors are supposed to be sort of infinite dimensional versions of the matrix algebra, so what would the guess be? Well, the guess is that you've precisely filled in all of the gaps, and then you get you take a 2-1 factor, and you take a set of all traces of projections, then you get the whole unit interval, the continuum. Right? So this is the sense in which these 2-1 factors are some kind of continuous geometry. There's a continuous notion of dimension. Dimension in the finite dimensional case would be discrete. Thank you. It's discrete in finite dimensions, and the 2-1 factors fill in this thing to give you a notion of continuous dimension. So you can have spaces of dimension 1 over pi for a 2-1 factor. Okay? So that's a fabulous and very seductive thing. In fact, von Neumann went on to develop a whole theory of so-called continuous geometries inspired by this wonderful continuity of the dimension in the 2-1 factor. To actually exhibit it, if you actually want to see projections with arbitrary traces, and that's not too hard either by Fourier analysis. If you take the free group on two generators and you fix a generator, you look at the algebra that generates, then by Fourier analysis, that just looks like L infinity, the circle, and the trace of a projection is just the measure of the set of all points where the function is 1, where the projection is 1. So it's very simple by spectral theory to exhibit projections of arbitrary traces in concrete examples. Von Neumann's theorem is that this is true in any 2-1 factor, and remember a 2-1 factor was by definition a factor with a trace, satisfying these three conditions. All right. Now, I'm going to change this, take a very slightly different point of view, and define the notion of representations of a 2-1 factor. So here we're going to switch points of view slightly, and it's kind of bizarre, but we're going to take a 2-1 factor, and remember, the 2-1 factor was defined on a Hilbert space. Okay, but now we're going to sort of free it from its Hilbert space. We're going to just sort of put it up there, and the Hilbert space is going to stay where it was. So we're going to think of it as an abstract algebra, okay, capable of acting on all kinds of Hilbert spaces. Capable of acting on all kinds of Hilbert spaces. So here we have a 2-1 factor. And we've made a psychological change. We've taken it away from its Hilbert space and think of it as an algebra and letting it act on other Hilbert spaces. And what I want to do is I want to give a number which measures the size. Let M act something different. So this always is a bit of a strange step. We have M, and by definition, it's acting on a Hilbert space. And we're saying, let it act on some other Hilbert space. Perfectly fine thing to do. And what I'm going to do is I'm going to turn the trace on projections into a notion of the dimension measured by M of this other Hilbert space on which it's acting. Right? So you can think in the back of your minds, if you like, the very simplest Hilbert factor of all is C. So this number that we come up with, dimension M of H, should be in the case where M is C, should be actually the ordinary dimension of a vector space over the complex numbers. So now how are we going to define it? Well, how do you define dimension of a complex vector space? You just say that it's the number of copies of C, that you say the number of linearly independent copies of C, the complex numbers that you see, right? That's the dimension. So you've done it by comparing your vector space to the one-dimensional vector space over the complex numbers. Okay? So dimension C of V, one-dimensional vector space, is you get it by compare V C on C. In particular, we take C on C, we take the direct sum of a whole bunch of copies until we hit the one that's actually isomorphic to V. And that number of copies is the dimension. Well, if we do it cleverly, we can do exactly the same thing for these 2-1 factors. But what we need is something to compare it to. Okay? So this is now a very important step. We're taking a 2-1 factor. We've freed it from, it was sitting on some ambient Hilbert space. We've taken it away from that Hilbert space. We've elevated its status to much higher than the Hilbert space. Now it acts on all kinds of different Hilbert spaces. We consider them all. We're going to take one, and we want to say how big it is compared to what? Well, we have to have a standard Hilbert space, something like the complex number dimension 1 vector space. Well, fortunately, that's available because we have the trace, and we do what's called this CNS construction with respect to the trace. So all I'm going to do is I'm going to say that, well, to get a canonical vector space on which M acts, just take M itself. M is an algebra, so it acts by left multiplication on itself. And that's sort of the one-dimensional object. If you want C acting on C, that's the one-dimensional vector space. The one-dimensional object is going to be M. But unfortunately, M is not a Hilbert space. It's not big enough. Right? Remember, I had those Hilbert space was this Goldilocks territory. Well, M is too small, Goldilocks. So we have to do to make it a Hilbert space, but we have, because of this condition here, we have exactly the data that we need to convert M to a Hilbert space. So what we do is we define an inner product of two elements. We use this data of the trace, this fabulous trace which produced continuous dimension, and we use it to define an inner product on the algebra itself. So this is x and y and m. With this, because of this condition here, M itself becomes not quite a Hilbert space, but a pre-Hilbert space. In order to get a Hilbert space, we have to complete it. And that we call, for various analogous reasons, we call it L2 of M, L2 of M with respect to the trace. We have a pre-Hilbert space, we completed to get a Hilbert space. Now M acts on M, and it's a very simple estimate to show that M actually acts on L2 of M. So this is the one-dimensional object. We've taken M itself and we've turned it into a Hilbert space just by adding some limits, and we've got the one-dimensional object. All right? Well, theorem about arbitrary actions of a 2-1 factor is that given any h, on which M acts, and we can write h isomorphic as an M module. Okay. Completely isomorphic as far as M is concerned to L2 of M plus L2 of M plus L2 of M. A bunch of copies of this, so K copies of this, plus the remainder term, which is L2 of M P. P is a projection. We have left multiplication, but we also have right multiplication. So we're perfectly happy to take L2 of M and apply a projection on the right to it. And that still becomes action on the left of M on this. So this here is a MX on the left. A multiplication on the left. Okay. So, what are we going to call the dimension measured by M of H in this case? Well, it's sort of, you'd be stupid to do anything else, but it's going to be K for the number of copies of this, plus we're going to get a real number measuring the size of it, P, trace of P. Yeah.
So P is a projector from M, or is it an arbitrary projector in L?
No, that's important. P is actually in M. Okay.
Slightly confused. For given to one factor, trace is unique.
Trace is unique, yeah. There's a lot of things I haven't been saying. Among them is the trace is unique. That's a very good question. The reason it's unique is basically because it's a factor. If you had a non-factor, then there would be lots of traces. But if you have a factor, then it turns out that by some averaging process, there's only one trace. Okay. That's getting into the technical. It's the elementary technical part of the subject. It's not very hard, but oh, well, it's a good point to bring out. There is only one trace. So everything is canonical. Right, so now all of a sudden we've got this dimension of any Hilbert space. This notation is completely justified. Obviously it's additive and it's continuous because, as we said, von Neumann showed that this trace is continuously varying So the dimensions of these Hilbert spaces are continuously varying. So this is sort of the best real way to understand the sense in which we've got continuous geometry here. We can have vector spaces of any dimension greater than 0, greater than or equal to 0. Pi, whatever. These are all possible dimensions of 2 1-factors. And, well, time is just too short, but I would like to make the digression of where this actually arises in the theory of group representations. If you take a discrete series of, if you take a lattice in a semi-simple Lie group and you take a discrete series representation, then the lattice generates a 2 1-factor, and the dimension of the Hilbert space of the discrete series measured by that 2 1-factor is actually given by the formal dimension of the discrete series representation. So if you know some representation theory of semi-simple Lie groups, then there's some really nice examples of this actually occurring sort of in real life, if you like. I don't have time to do that properly, because I want to now get on to the first main topic of the course, I guess, which is index for subfactors. Up until now, we've done sort of a fairly light introduction to the theory of polynomials. We don't really see why 2, 1, we haven't seen anything other than 2, 1-factors, but that'll slowly come. So I want to define a notion of index. I want to motivate this fairly carefully. So the motivation will be given by a important example, which is, subfactor is obvious, right? If we have a 2, 1-factor, then we can have a smaller one, which is also a 2, 1-factor. That's the definition. The only thing I'll point out is that you might wonder whether the identity is supposed to be contained in it. Well, depending on your definitions, that's automatically true, but I'll just insist. We're looking at subfactors which contain the identity. Okay. So let's think of examples. Well, there's the trivial one, which is n equals m. If we're trying to define an index, that should have index 1. Right, so this is the first requirement. However we define this beast, this had better be equal to 1. Okay. Right, now let's go to another one. M, let's suppose that M is the K by K matrices. N. So N, in this case, the small one is a subfactor, the big one, by considering diagonal matrices. All right, so let's just get some intuition going here and ask ourselves the question, however we define this, what had better be the answer for this case? I'm just appealing to your intuition. What is this index going to be? It's supposed to be sort of how big. We think about fields, right? If you define a degree, if you have an extension field, what's the degree of the extension? Well, it's the dimension of the big field as a vector space over the small one. The number of linearly independent copies you see of the small field in the big one. So this should be the number of linearly independent copies of n that you see in the K by K matrices, which is K squared. So however we define this, that better be our answer. All right, so now let's go ahead and define it. Well, it's not very hard with everything that I've said. Remember we have M actually has this canonical Hilbert. We have to work in Hilbert space to use von Neumann theory. So we take this Hilbert space, but N being a subalgebra of M means that this becomes a left N module by restriction. Okay? And this notion that I said here, the number of copies of N inside M should be, obviously, the dimension measured by N in the von Neumann sense of that guy there. So that's our definition. So obviously mm is equal to 1. That was the way we normalized the dimension. And obviously this is true also because we can see the decomposition of L2 of m in this case as the direct sum of k-squared copies of n, L2 of n. So we've got an interesting notion. Let's do another example. This is moving in a very Japanese direction because this theory was initially was founded by people in Japan. N equals the fixed point algebras under G. Right? So this is a sort of Galois theory approach to the whole thing, and I think the names that come to mind for me are Nakamura and Takeda and Suzuki. And there's probably others that I'm forgetting, but they developed a Galois theory for these two unfactors. So the idea is we think about them as being fields. We have groups, actions of groups on them, and the obvious example of a subfactor here is n equals the fixed point algebra for G. These Japanese actually show that the Galois theory worked quite well. There's a Galois correspondence between intermediate subfactors and subgroups, and all kinds of nice things. The normal basis theorem, all kinds of nice things are true. So, what is the answer in this case? Okay, well, you know, you can't quite see it, but, you know, once again, this is intimidation. Mathematics would just not work if this were not the answer, right? It's got to be the order of the group. To actually see a decomposition of G, of M as G copies of N, it's actually this normal basis theorem, which was proved by a combination of the early Japanese pioneers. Right, so now let's think a bit about what we've got here. We've got this notion of index. It's defined by von Neumann dimension, and remember the great thing about von Neumann dimension is it's any real number bigger than 0. So now on the other hand, m is bigger than n, so this index has to be at least 1, right? It's got to be at least 1. Can't have anything smaller than 1. So now we look on the example side and we see, well, we've got the squares of integers, and with G we have integers. You'll have to take my word for it that it's very easy to fix up situations where G acts appropriately on to one factor for a finite group G. I guess part of this assertion was also that this is also a factor. Now actually it's not always true, but the word is outer. The group has to act in an outer way on M. I'm suppressing a few simple details there. But there are plenty of such actions. So what was I getting at? Well, I was getting at the fact that we're getting integers. And you can fiddle with these constructions and mix and match and take subgroups and so on. You always end up with integers. On the other hand, it's supposed to be a real number bigger than 1. So the question is, which is it? And here is the theorem that started off this subject, I guess, is that so you sort of get either it's any real bigger than 1 or it's all integers, but the theorem says it's not either of those, and the theorem says that if m is less than 4, then it's 4 cosine squared pi over k equals 3 to 1. So on, if greater than no restriction, A. So the answer is sort of, you know, the discrete property that we were seeing is true, and the von Neumann continuous dimension is also true. It's just a question, these are two regimes. And to actually draw this set of numbers, it's going to be important for the rest of the course. Here's the continuous part from 4 on, and the discrete part, if you do, once upon a time one learned this in high school, 4 cos squared pi over 3 is equal to 1. It was an easy calculation. Maybe it still is in Japan, I hope so, for Japanese mathematics. And the next one is 4 cos squared pi over 4, which is 2. And then 4 cos squared pi over 6, which is 3. And then here we have the first really good value, which is 4 cos squared pi over 5. And in some high schools, not mine, you learn that this is the square of the golden ratio. And they converge up. So the answer is this thing that's hauntingly like a quantum system with bound states and free states. I don't think anyone has ever managed to make sense of that properly, but that's the answer. So the answer is that the index is restricted to these values if it's less than 4, whereas from 4 on it can be anything. And these two are all together make up part A of the theorem. The theorem would be useless unless there was its part B, which says that all values are true. Right. So for any real greater than 4, or for any one of these numbers, 4 cos squared pi over n, I can actually construct a subfactor having that value as its index. So this, this used to be a pretty surprising result, and I suppose it still is, really, if you haven't seen it before. I think I've done all the ingredients. So I said that I was no time to prove anything in this course, but now I sort of have to, in order to progress, I have to sort of wander into the proof, because all of the subsequent structures and interest and the connection with knot theory and statistical mechanics and so on, all going to come out of the proof. I won't actually give all the details of the proof, but we've got to at least see how it goes. Now this is the original proof I'm going to talk about. There are sort of possibly slightly shorter proofs available, but it's a good thing that that wasn't done in that way, because a lot of good stuff would have been missed completely. These proofs are only really available with hindsight. See, the point is this, that we're dealing with an arbitrary subfactor of a 2-1 factor, and hopefully I've sort of scared you a bit about these guys. These are infinite dimensional simple algebras that are of quite a bizarre nature. They have this continuous dimension. They're not like all operators. They're something but upsetting. And this is just sort of an arbitrary sub-one of them. So where do you get started trying to prove this thing about it? And the index is just the number of copies you see of this and that. Where do you start? Well, you can start making hypotheses about it, but as soon as you make a sort of nice hypothesis, you end up proving that it's an integer. That's no good. So there's got to be some kind of universal construction that is always available. Unfortunately, once again, it's a Japanese source, Umegaki. One thing that always exists, whenever you have a subfactor with 2-1 factor, is the so-called conditional expectation. Okay, so what is it in the concrete cases? Obviously, it better be something you understand. In the case of the k by k matrices, you just project onto the diagonal. In the case of the group, a fixed point algebra by group, well, you know, if you've done a Galois theory course, you don't have to guess very much. You just take the average over the group action. That's the conditional expectation. But the point is it always exists, and the proof that it exists is very simple. You work on the L2 level. L2 of n is sitting inside L2 of m. This is a closed subspace of this Hilbert space. Therefore, there exists orthogonal projection. Hilbert space has orthogonal projection. There exists E sub n. And you simply show that E sub n, this orthogonal projection, preserves these dense subspaces. It sends m to n. Okay? And that explains why it's called a conditional expectation, because if you were doing probability theory, then you would do, there's this thing that if you have a sigma algebra and a sub-sigma algebra, then there's always a conditional expectation. And how do you prove it? Well, you go to L2, you use the L2 property, and then you show that the L2 projection preserves the sigma algebras. Fantastic. So it's exactly the same proof, exactly the same idea, so it's called a conditional expectation. And we get a hint that this whole theory of 2-1 factors, maybe even polynomial algebras, is some kind of non-commutative probability theory. Okay. Anyway, it always exists for these abstract reasons. So let's do what we can with it. Do what we can with it. This, we come immediately to the so-called basic constructions. So what we're going to do is we're going to simply take all of the constructions that we have so far for the 2-1 factor, throw them into the mix and see what comes out. So what do we have? We have m, we have n, we have, well actually this is the algorithm better. Here we have m, and here we have this subfactor. So if you're still Galois motivated, this is a field, subfield. And the construction that we're going to do could have been done by Galois. So what do we have? We also have L2 of m. Trace. L2 of m. M is acting on the left here. It's also acting on the right. We'll observe that. Since n is a subalgebra of n, it's acting on the left. It's also acting on the right. And we have this conditional expectation. So how's that acting? Well, it's taking this thing here and projecting it down onto this. It's taking this and projecting it down onto that. So it's some operator that's not in the picture. So we take it and we throw it into the picture, acts on L2 of m. And we take the polynomial algebra generated by m. It has these two identities. One is as a map from m to n, and the other one on the L2 space. Well, things acting on the L2 space, we should call it little e sub n. Okay, and then we have this m on the right. So this we could call this m on the right. Right, so I've introduced a notation. A better notation to start with would be this one. Remember I said that the commutant of the commutant is actually the polynomial algebra generated by this thing. So this is the definition. All right. Well, you know, if you just stare at this picture for a while, then certain things start to suggest themselves as to what might happen. And the first thing is, if you take an algebra and you look at the left with an identity, then what's the commutant of left multiplication is right multiplication, trivially. So the first thing that is true is that this thing here is the commutant of this thing here. So what's this guy? It's bigger than the commutant. So it has a chance of being the commutant of this guy. That's true. So another way to do this is right in. So all of a sudden, it's, you know, just to fill in this picture, there's a very natural construction which is taking place, and this construction was known before I worked with them. It was known to a lot of people. Certainly Eric Christensen had done some deep work on it. Scal also used it. But from this point of view we're coming at, it's sort of the only thing that we can do. You know, we're stuck. You know, we have this canonical thing, so let's throw it in and turn the handle and see what comes out. Well, what comes out is this really beautiful sort of duality. Turns out that you can show that not only this is this the commutant of this, that makes it a 2-1 factor, but the index of this and this is the same thing as the index of this and this. So to every subfactor, we have a canonical extension of the same index. So that's the theorem. So this is all supposing the union is 1. So n is equals n right commutant 2-1 factor. And so it's as if we've taken M and we've put a mirror there, reflected it, we've taken M and it's become, instead of being a subalgebra, it's become an extension. Okay? Beautiful, beautiful symmetry. Now, you may ask, well, I said Galois could have done it. Why didn't he? Well, if you did Galois theory, and M was a field, and N was a field, then this thing that you get is the same thing as taking the algebra. I mean, people in Galois theory do this, don't get me wrong. You're taking the algebra generated by the big field and the so-called trace in Galois theory onto the small field. Well, that's not a field. It's non-commutative. Okay? So Galois didn't do it because you start in fields, you get out of fields. But here, we start in 2-1 factors, we stay in 2-1 factors. So it's a very natural construction. Wouldn't miss it. No, you might miss it for 10 years, but eventually, hopefully, you see it. Okay, so immediate consequence, the index cannot be between 1 and 2. So this is the, this is a surprise, right? We were expecting it to be a continuous full Neumann dimension, and now all of a sudden we claim that it's between 1 and 2. Well, this is completely obvious in this whole picture. In fact, I'm not even sure that I needed the basic construction to deduce this, because we. I think I'm not even sure I need it. I think I can just show this immediately, because you can write M as N direct sum its orthogonal complement. Let's do it on the L2 level. Plus this is the orthogonal complement. Okay, so how does the dimension work? We'd want to take the dimension of n. This is 1, right? And this is something. No, it's not clear that that has to be bigger than 1. Okay, so sorry, I have to take that back. This it does require a little bit of the basic construction. Since I didn't prepare this, I won't attempt to do it. But it follows immediately that this has to be at least as big as n. So the index has to be at least 2. I should say, I always find this very amusing that shortly after discovering this result, I found a beautiful proof, beautiful construction that the index can be any real number from 1 to infinity. Which is the opposite statement. So luckily, I had this proof first, and I was able to find the flaw in the other rather beautiful proof of the opposite, which still has considerable interest, but just wrong. Okay. So, yeah, I'm sorry, I thought I could do this completely trivially, but it needs a little bit of... It's very elementary manipulations in this so-called basic construction. You can deduce that the index is between 1 and 2. Right. So, actually by iterating it again, you find that 2 is isolated. That in fact, there's a little interval on the other side of 2 that you can also exclude. Because if it wasn't, you could get back to something. Anyway, you can get quite a bit of mileage from this, just from this basic construction. So you can never get beyond this value. You can pretty much exclude everything up to 4 cos squared pi over 5 to the golden ratio. But you can never get beyond that. Okay, and I tried very hard to get beyond that because I thought it was an integer, but everything failed, and there's a good reason that it failed because there is actually an index, a subfactor of that index. Okay. But after all this playing around with this basic construction and looking at it in 101 different ways, the natural thing came to be to iterate it. The power. So remember, so let's see what we started. We started with this canonical construction. Canonical construction to give us an extension, a dual extension, right? And one of the properties of that dual extension is that this one has the same index as this one. So now we can forget about this one and do the canonical, this basic construction again. You get something which in this notation would be M. Okay. And by doing the same kind of slightly more complicated manipulations that gave this gap between 1 and 2 here, you can get the gap all the way out to 4 cos squared pi over 5 and the fact that that is isolated by doing 2 of these. So then it's clear that, the game is afoot and just keep on doing this process. Now the notation is completely out of hand, right? The next one would have all of these brackets. So we define it by a single difference equation. In 2 factors, we define n sub k plus 1 to be the result of applying this basic construction to e sub mk minus 1, and then we have the initial condition saying n0 is n. So here this would be n0, n1, then n2, then n3. This was not the original numbering for obvious reasons. One thought of this one as being the first, but for lots of good a posteriori reasons, this is the right way to number things. Okay? And out of this, you can get a proof that in several different ways, you can get a proof that the index has to be one of these values, less than 4. However, I don't want to emphasize that proof. I want to emphasize the real gift of this proof to mathematics and to me, personally, was that the first thing that you get out of it is these e's. We call this one E1, obviously. Now we can say we have a renumbering E sub m sub k minus 1. We're going to call E k, I think. So anyway, the first one is supposed to be E1. We number the e's. Each time you do one of these basic constructions, you get out a new projection. We number them, so the first one we got is E1, the second one is E2, the third one is E3. So on. Okay, well, this was a canonical construction, so these E's satisfy some canonical relations, and here's what they are. They're projections by their very definition. This commuting process is very simple. It's just if we did the next step, then the E that we created would actually commute with this E. This is just some simple property of conditional expectations. And then the third one.
But normally, I mean, they act at different spaces. So how do you extend the smaller ones to the bigger spaces?
Right, that's a good point, and it's what makes this a bit of a pain in the neck as to work with doing it this way. They do act on different spaces, but ultimately they end up in the same algebra. Right? We forget about the spaces they're acting on. They're actually coming up in algebra. So E1 is in this algebra, E2 is in the next algebra, E1 is in the third one. All the algebras are included. So all the EIs.
So relation B holds only after restriction to the domain definition.
No, it just works. They're in an algebra, and this relation B is just true. To prove it is a bit of a pain because, as you said, you have to worry about what, I'm picking up the whole vector space. But it's, once you've got over that little bit of psychological difficulty, it's not very hard. It really just comes back to this fact that what you do is a sort of Markov type property, that what you do is independent of what you did a couple of steps ago. That's a very good point. What's a pain about this is that every time you do this basic construction, you're acting on a new Hilbert space. On the other hand, the algebras themselves are embedded one in the next. So these things make sense independently of what Hilbert space you're acting on. You can just choose a large enough one. And here's the last condition of some interest. What happens when they're next door? And let me just complete the table and I'll stop for the day. So these relations themselves are quite precious. They're actually first run into probably by Frobenius, but certainly explicitly by Baxter and other people in an understanding of a paper by Temperley and Lieb. So these are called the Temperley-Lieb relations. But there's one more, which is, remember, everything's a 2-1 factor. All of these algebras are 2-1 factors. And 2-1 factors have a unique trace. There's a canonical trace. And to complete the story, obviously you're going to want to know what the trace is on these EIs and words on the EIs. And here's the answer. And this is this amazing Markov-like property. Trace of WEN plus 1 equals 1 over the index. Trace of if W is a word. Okay, so that's if you have a word like E2, E1, E3, E2, and then you multiply it by E4, and the trace of that is the same thing as the trace of this one. And it's a really amusing exercise to show you that inductively this formula tells you how to calculate the trace of any word on the EIs. That's the key, the technical key to actually proving this 4 cos squared pi over n thing. Okay, but I'm already a little bit over time, so I'll stop there for today. So next time, it's Monday, I think, right? Monday afternoon, 3 o'clock, I will point out what nowadays is supposed to be obvious, which is that this thing here, these relations here have something to do with the braid groups, and the fact that this also has something to do with the braid groups, and I'll deduce the existence of a polynomial invariant of knots and links in 3 space, which is sort of a bit of a surprise. So far we've got nothing whatsoever to do with any kind of finite dimensional topology. Okay.
I have a personal question.
Okay. We have a question.
So how long do you take to get over basic concepts
okay.
You take to get this proof.
Yeah, okay.
After you also.
This is a very good question for students, I think. You know, how long does mathematics take to do, right?
So let me sum the whole thing up.
So this is just a anecdotal, this is how it happened to me, this is how I lived it. So I had the idea of index for subfactors in 1976. 76, right. And there's even a paper, I think. I called it something else. I call it the Suzuki-Goldman invariant. And then there was the question of whether it was a real number or whether it was an integer. And I was just a really quite young graduate student in 76, and I ran into experts in the subject, and every time I ran into experts, I say, what's the story here? Is this an integer or is it a real number? And I got no answer. Some of them said, well, that's an interesting question. Some of them said, that might be an interesting question. And some of them said, that's a stupid question. So, that's a lesson to the students. Don't listen to the experts and don't know much, really. So, the experts are already channeled into their expertise, like I am. So don't listen to them if you have an idea. So, that was in 76. Then I so I did my thesis, and I had this, and this was my background problem. It was related to the thesis. My thesis was on these group actions, so it was good. So, and then in 1980, I realized that the basic construction was key. And I proved in 1980 that there was this gap between 1 and 2, and I also proved that you could get this continuum from 4 on. That's a simple construction. I haven't gone into it here. So it was a really interesting question at that stage. I tried to publish that result. It was rejected, and I'm very glad it was rejected. It was rejected by Canonical, who said, it's a nice problem. You made a good start. Solve it. So that was very good advice. And the person who took the most interest in it was, once again, Japanese, was Masamichi Takasaki, who was really quite fascinated by this and wanted to know the answer. So I moved to UCLA in 1980. And for the next year or so, I sort of thought about not much else, seriously. And it was in 1981 that I actually got the answer. Late 1981. So that's 5 years after, almost 6 years after I posed the problem, and thinking about it a lot. I got this idea of iterating the basic construction, and then it all sort of came out. It was great. Interest and excitement, and by 1982 it was really proved, and it appeared in 1983. So in the meantime, there was the knot theory connection. So the connection with braid groups, I went to visit my friends in Geneva where I did my PhD, and there they knew all about braids, and as soon as I wrote down this equation, they said, oh, that looks a bit like the braid group. And so it's not the braid group, but I thought about it for a while, and then I realized that you can turn it into representations of the braid group. That was in 1982. Okay, now, the mathematical world has changed. In 1982, there was absolutely zero interest in linear representations of the braid groups. I assure you, it may sound strange today, but it's true. No one would give me the time of day with these linear representations of the braid group. It was just, So I sort of, lots was going on in subfactors, so I sort of dismissed it. But until 1983, when I started analyzing these representations very carefully, that just means more study of these EIs, and I realized that at index 3, the image of the braid group was actually some finite simple group. Turns out eventually not incredibly exciting finite simple group, but to me, not knowing anything about them, these were pretty big, a couple of million elements in the group. It seemed pretty amazing that this was coming out of this. So I kept on. I plugged away with the linear representation, even though no one else would listen to them. Then in 1984, I decided I had to talk to, real braid group people. And I went and saw Joan Berman, and I told her about all these representations and so on and so forth, and she was totally uninterested also. So, you know, even the world's big expert on braids was not interested in my stuff. However, she did explain to me a few things, and one of them was this correspondence between knots and links and braids. And then about a week later, I realized that this property here just meshes magically with the braids and links. And that was so in 1984. So from the 1976 to the sort of finished product was really in 1984. So it was 8 years to